Hi everybody, welcome to the start of our solar system discussion. So our solar system is quite a unique one in that it is the only known solar system with life. So we're just going to have a quick tour at the beginning, and then individual videos and PowerPoints will follow with each of the individual planets that we will discuss in more detail. So make sure that you are familiar with this material, though, because this builds the foundation for the rest of our discussion of the solar system, and to some extent, our discussion of some of the future units. But you don't really need to know particularly numerical details, although certain things about relative distances from the sun I kind of recommend knowing just to give yourself a picture of how planets appear with respect to the rest of our solar system. So here's a nice picture of the zodiacal light, and under very dark skies it's visible as a cone coming from near the western horizon after dusk, or from the eastern horizon maybe a couple hours or so before dawn. It's caused by sunlight scattering off of dust grains that are either being emitted from interplanetary comets that are visiting the inner part of the solar system, or, as we found more recently, a lot of it is being caused by dust being blasted off of the surface of Mars by meteorite impacts. So some introduction, at least motivational introduction to this, is to bear in mind that the world tends to pass through approximately 500-year cycles of exploration of bigger and bigger things. So 1,000 years ago, there was a big push into exploring other countries and conquering them, and basically exploring the rest of your continent. And then, about 500 years ago, the push became toward exploring the rest of the world. And nowadays, the push is starting to be exploring the rest of our solar system. So who knows, given future technology and breaking what we believe to be known laws of physics, what might happen 500 years from now. But in any case, as the World Space Agencies continue to send new probes throughout our solar system, we are gaining knowledge of how our solar system came to be and whether we are actually the only life forms in our solar system. And therefore, we are gaining more insight into the question of why we are here. So some quick facts about our solar system. It is obviously dominated by our sun. It formed 4.568 billion years ago. We'll get to how we know that later on. And it originally, we believe, had more planets, but some were ejected and crashed into others during and after formation. Obviously, there's a very large variation in size, density, and many other characteristics of the planets. And as we know, it's the only known solar system with life, and some would say it's the only known that there are still no known solar systems with intelligent life. Some other facts. The total mass is about 2 times 10 to the 30th kilograms. That is 2 million trillion kilograms. And it's dominated by the sun, which makes up 99.86% of the mass of our solar system. The largest planet is Jupiter, which is over 300 times the mass of Earth. But even Jupiter makes up only about 1/1000th of the mass of our solar system overall. Smallest planet is Mercury. The most intelligent planet, with an average IQ of 100, is Earth. The hottest planet, strangely enough, is Venus. We're going to get to why in a lot more detail when we discuss Venus, even though Mercury is closer to the Sun. On average, the coldest planet is Neptune. Now, the inner planets, which are generally called the terrestrial planets, are Mercury, Venus, Earth, and Mars. These tend to be rocky, they have small masses and radii, and generally they are warmer. They don't have any rings, and they have few, if any, moons. Mercury and Venus have no moons, Earth has 1 moon, and Mars has 2 little moons. And generally speaking, you can see a solid surface on these, at least if you look through either visible light or infrared light, because Venus has such thick cloud layers that you need to look at longer wavelengths in order to be able to see the surface. But still, the height of Venus's atmosphere compared with the overall radius of the planet is small, whereas with the giant planets, it's quite different. The largest of the terrestrial planets is Earth. So we are the largest of the terrestrial planets. Mercury is the smallest. After all, it's the smallest planet in the solar system. The hottest is Venus. It's hot enough to melt lead there. On average, though, the coldest is Mars, although the coldest temperatures that are recorded on terrestrial planets actually occur on the nighttime side of Mercury, the closest planet to the Sun. Most active geology exists on Earth, though we're now realizing that Venus has relatively active geology. It doesn't have active plate tectonics, but it does have active volcanism. and Earth is the only inner planet that has a large moon. The outer planets, also known as the giant planets, sometimes called the gas giant planets, though nowadays people like to separate the giant planets into the gas giants of Jupiter and Saturn and the ice giants of Uranus and Neptune. These tend to be much larger in size. I mean, the smallest of them, Neptune, is almost 4 times the diameter of Earth, and they are not nearly as dense as the terrestrial planets. The bulk of their mass is made up of hydrogen and helium in various forms. They all have ring systems, and they all have lots of moons. And many of these get a large portion of their heat from internal sources. In other words, they don't get the majority of their heat from the sun, which is kind of neat. Now, the largest, of course, is Jupiter. Jupiter is the largest planet of the solar system. The least dense planet is Saturn, which, if you had a bathtub big enough, the joke is it would float, but hey, it might leave a ring, haha. Uranus is actually rotating on its side. Its axial tilt is 98 degrees, compared with Earth's 23.5 degrees. And we'll get to why in more detail when we talk about Uranus and Neptune. So these outer planets, as I mentioned, are called the giant planets, often divided into gas giants and ice giants. Uranus and Neptune are often called ice giants because a large portion of their mass inside comes from various ices, like water ice, methane ice, ammonia ice, stuff like that. In fact, in the case of Uranus, Uranus may have multiple Earth masses worth of water ice in various forms. So Mercury and Venus actually have no moons, as we mentioned. Earth has 1 moon with the nice romantic name of Moon. And Mars actually has 2 moons, but they are very small moons. The largest of them is small enough such that if you're not careful, you could run into orbit around it. Jupiter has 79 known moons, but it only has 4 big ones. After the 4 big ones, the next ones are very, very tiny in size in comparison with even the 4th biggest one. Saturn has the most known moons of any of the planets in our solar system. It has 82 moons with established orbits. 53 of them, as of the time of this video, have names. And Saturn also has a bunch of little moonlets that are embedded inside of the rings, and we'll talk about how we know about those when we talk about Saturn. Uranus has 27 and Neptune has 14. Some of the smaller bodies in our solar system actually have moons as well. A number of the asteroids have moons, as well as a number of the Kuiper Belt objects that orbit out past Neptune. So, the first asteroid to be discovered to have a moon was the asteroid Ida, which has a little moon called Dactyl. But even the dwarf planet Pluto has 5 moons, another dwarf planet Haumea has 2. In fact, there are a number of other objects that most people have never heard of in the Kuiper Belt that have a number of moons. Relatively small objects quite often. In fact, it turns out that the small objects are the ones more likely to have moons. We'll talk about why that is when we talk about asteroids. Here's a picture of Ida and its little baby moon Dactyl, which is only about 1 kilometer in diameter, the moon that is. And there is the moon system of Pluto. The big one, Charon, is depicted at the bottom. Well, not depicted, this is a picture of part of it. And the other 4 known moons are shown here. Pictures taken by the New Horizons spacecraft when it sailed by in July of 2015. Now about some of these moons. The largest moon in the solar system, Ganymede, orbits around Jupiter. And we'll talk in more detail about Jupiter's moons as we get into discussing Jupiter, because a lot of them are quite interesting. Ganymede is actually larger in size than the planet Mercury, so is Saturn's moon Titan. Jupiter has another moon, Io, which is actually the most volcanically active body in the solar system. And the next moon after Io in Jupiter's system, Europa, has more liquid water underneath its crust than all of Earth's oceans combined. In fact, there are probably several moons in the solar system for which that applies. Ganymede may even have more water than Europa. And Saturn's moon Titan probably does as well, but even more interesting in some minds about Titan is the fact that it has a very dense atmosphere. Meteorology is important there, and it has liquid on its surface. And Neptune's moon Triton has ice geysers, and it's actually believed to be a very good model for Pluto. In fact, underneath the crust of both Triton and Pluto is probably either a liquid water ocean or liquid water in some form. So about the rings, all the giant planets have rings. Jupiter has them. Saturn obviously has the most complex system. Uranus has a system that's kind of more rocky rings, and not really as visible, whereas Saturn's are formed mainly out of ice. And even Neptune has a set of rings. In fact, as we'll discuss when we talk about Neptune, in something like 100 million years, Neptune will have probably the most spectacular ring system in our solar system. Now, how do rings form? Large rings, like those around Saturn, occur when a moon passes inside of a planet's Roche limit. The Roche limit is the point inside of which a body will be torn apart by tidal forces. The idea is that a planet gets held together by a combination of solid body forces and gravity. But gravity, remember, goes as 1 over distance squared. So if you take the same mass of an object and just put it over larger distances, then the force of gravity will be weaker at the surface of the object. Although, of course, if you just build more material onto that object, then the force of gravity will get stronger because you're dealing with more mass as well. So the force of gravity, if you just imagine a body getting bigger and bigger and bigger, actually goes as the size of the body. But here's the thing. Remember that tidal forces, which we've discussed in the past, go down as 1 over distance cubed. So as you get farther away, the tidal forces from the planet itself get much, much weaker. But as you get closer to the planet, they get much stronger. So we're talking about an R cubed type of force law there. So it turns out that when you take into account the 1 over R squared force law of gravity and the tidal forces of pulling a body apart of 1 over distance cubed, it turns out that for a body of given density, the distance in which the tidal forces will overwhelm the forces of gravity is independent of the size of the moon. So for a moon of a given composition, if it gets inside of a certain point, tidal forces are going to overcome the forces of gravity holding the moon together, and the moon will get pulled apart. So that's something to keep in mind, because a whole lot of the moons in our solar system are made out of ice. And ice has a certain composition, meaning that the tidal forces will act a certain way, and it will be independent of distance. So as a result, if you have an icy moon getting close enough to a planet, it's going to get pulled apart. After it gets pulled apart, the particles go into orbit, and they kind of ground each other down so that you end up having very fine particles. In the case of Saturn's rings, we're talking about 99% of very fine ice particles, 99.7% in fact. But things get flattened out because of the vertical collisions with respect to the motion, so that kind of damps out any vertical motions. So Saturn's rings, as it turns out, are extremely, extremely flat. So they're not going to end up being able to form a moon, though, because they're too much inside of the Roche limit. So any attempt to form together a moon would end up just getting pulled back apart again. Quick characteristics of the planets. So again, you don't really need to know these, although I would actually recommend knowing approximately how far each of the planets orbits from the sun. And by approximately, I mean saying, okay, Mercury orbits at about 0.4 times the distance of Earth from the sun, Venus about 0.7 AUs, Earth, of course, is 1 by definition, Mars is about 1.5, Jupiter's about 5, Saturn is about 10, Uranus is about 20, and Neptune is about 30. I would recommend that because these will give you a good way of visualizing the places of our planets in the solar system relative to the sun. In terms of the masses, yeah, you should know that Jupiter and Saturn are the most massive ones, and that Jupiter is the most massive overall, and the Mercury is the least massive. Notice that Mars is actually not all that massive. Mars, it turns out, is a bit less dense than the terrestrial planets, and we're still working on the best explanation for why that is, but it's the least dense of the terrestrial planets, so denser than the rest of them. Earth is actually the densest, though Mercury, strangely enough, is composed of the densest material. So why isn't Mercury the densest? Well, remember that Mercury is less massive, so it has less of gravitational pull, and therefore less gravitational compression than Earth has. Saturn, the least dense, less dense than water. And notice Uranus isn't all that dense either. So now it's time to move on and look into how our solar system formed and the general characteristics of the bodies that resulted from that formation. So to understand how our solar system formed, we need to look a little bit into how our sun formed, because how stars form has a lot to do with how the planets form as they go around the sun. So first of all, why would we study this? For one thing, it's cool. It also helps us to understand other processes in astronomy and astrophysics, and also understand the processes behind the formation of Earth and its subsequent evolution. In other words, geologists would care about this as well. And it might help us shed light, on understanding the future of the solar system, that having a lot to do with the future of our sun. And understanding how planets formed in our solar system will also help us to understand how planets form around other stars. How do we know this stuff? Well, a lot of it is guided by theoretical underpinnings, that is, mathematical understandings and putting together various theorems, theories, etc. into a coherent understanding of our solar system, as well as numerical simulations, that is, computer simulations, and observations, seeing whether our ideas are borne out by looking at newly forming solar systems around other stars. So how do stars form? They all form from the collapse of giant molecular clouds, or GMCs, so giant molecular clouds. And essentially these are large nebular objects that are massive enough to collapse and form stars. They're mainly composed of hydrogen and helium. Remember, hydrogen and helium were the elements that formed during the Big Bang. They compose the great majority of the mass of ordinary matter in our universe. Now, heavier elements, what astronomers call metals, according to an astronomer, anything heavier than helium is a metal. These seed these giant molecular clouds, and these help to form structures in them and allow the giant molecular clouds to collapse more quickly. And then they get spread throughout. These heavier elements are formed in the first place from previous generations of stars that spread them throughout the universe through supernova explosions, as well as casting off their outer layers in normal lives later in their lives, stars that is. Our sun will eventually do that, just a slow, gradual casting off of its outer layers, which will pollute the rest of the galaxy with dust. Now, this image that I showed back here is a picture of the famous Orion Nebula. This is the closest large giant molecular cloud to our solar system. It's about 1,500 light years away, and there are over 1,000 stars currently in it. In fact, there are 4 that are easily seen with binoculars or a telescope. But one that is much larger than the Carina Nebula, but one that is not visible from mid-northern latitudes like Northern Virginia or the DC area, is someone called the Carina Nebula. However, if you go to southern Florida, you can see the Carina Nebula. Now, the Carina Nebula is much farther away. So, if it was actually at the same distance to us as the Orion Nebula, it would be 30 degrees wide in the night sky, and it would be bright enough that you'd be able to see it during the daytime. This is a picture of part of the Carina Nebula. And indeed, this area right here, called Eta Carina, is composed of a couple of stars, each with over about 50 times the mass of our sun. And I think one of them is over 100 times the mass of our sun. The most massive of those is on many astrophysicists' list as probably the first among the stars that we know of, the most likely that would be potentially able to go supernova during our lifetimes. So in other words, like if you were to ask, like, okay, among all these stars that are eventually going to go supernova, like Betelgeuse, Rigel, Bellatrix, Antares, Eta Carina, etc., which of them would be most likely to go supernova during our lifetimes? And they would generally reply with Eta Carina, because this thing's really near the end of its life. However, we're going to come back to this cute little thing right here, because it's stuff like this where stars are still in the process of forming. So how do these gas clouds collapse? Remember Newton's law of universal gravitation. Gravity affects everything. And the force of gravity goes infinitely far. It does get weaker the farther you go, though. So it's like, okay, why don't thunderstorm clouds collapse on Earth? Well, the problem is gas pressure. Thunderstorm clouds don't collapse on Earth because the gas pressure is much, much, much greater than the force of gravity. However, remember, as you pile more and more material onto your object, the mass goes as size cubed, which means the force of gravity overall would go as size cubed times 1 over size squared because of the inverse square law. So overall, the force of gravity as you keep piling more mass onto an object and making it bigger, is going to simply grow in accordance with the radius of the object. So eventually, if you start putting more and more mass into a giant molecular cloud, or imagine it just going farther and farther out, eventually it will reach a size where the inward pull of gravity will overwhelm the outward push of gas pressure. And when that happens, it will collapse and form stars. Now, the mass at which gravity inward balances out gas pressure outwards is something called the Jeans mass. And it's not really something that we need to worry about so much in here, but the point is that this can be derived without a whole lot of effort. So long story short, gravity attracts everything, and if you have a gas cloud that is able to collapse, it will collapse within about 10 million years because of its own gravity. But the question is, what initiates the collapse in the first place? After all, shouldn't all of the gas clouds collapsed way back? Well, generally speaking, they did, and they formed the parts that would eventually go into forming the Milky Way galaxy. But some of them were kind of borderline. Things like the Orion Nebula region were kind of borderline, and so they wouldn't really be able to collapse until something else kind of pushes them over the edge. So this is part of the Equinebula, and you can see that something seems to be kind of sculpting this, and the idea is that if you have something that does form stars, well, the most massive stars will become supernovae, and these supernovae themselves will generate shock waves that can help promote further collapse. Now, for large giant molecular clouds that hadn't collapsed before, a lot of times this will occur when these things move through the density waves that are traveling outward from a rotating spiral galaxy. The places where gas clouds and everything go through these density waves, well, where that happens, they get compressed one way, extended another way. That results in a general collapse and star formation. Well, where that happens is, and just tracking it as the galaxy rotates, you end up creating spiral structure. That's the origin of the visible spiral structure that we see in our galaxies. Notice the spiral arms tend to be bluer because these are where the stars are in the process of forming. Bluer stars are younger stars, as we will discuss when we talk about star formation in a future unit. Young blue stars are hot stars, and they're hot because they're more massive, but more massive stars go through their life cycle much more quickly than stars like our sun. And as I mentioned, supernova explosions can also cause particularly individual parts of the cloud to collapse. And also tidal forces due to galaxy collisions. For example, in this case, this is a situation where you have everything kind of working just right. You have this satellite galaxy around M51, also called the Whirlpool Galaxy, that is just kind of helping to carve out these spiral arms in terms of really helping to propagate, causing these density waves to propagate outward from the center that so often do in the case of spiral galaxies. Now, here's a situation where you have two roughly equal-sized galaxies in the process of a collision, and the tidal forces there compress the gas and cause rapid bursts of star formation. In fact, you can also see a whole lot of dust here. That dust is being spewed out by all these supernova explosions from these young hot stars that are being created in these bursts of star formation. But in any case, after the cloud starts to collapse, kind of looking at it, say, a little bit more closely, you realize that the density in a collapsing gas cloud is not uniform. Some parts are going to be denser than others. And the parts that are the densest are going to become the seeds for future stars. So keep this in mind. Because of the fact that the parts of the giant molecular cloud that are densest end up forming stars is going to become important because, just remember that the area near the star is going to be the densest part. It's going to be composed of the densest elements, and it's going to be composed of the densest material. In other words, you're going to have more atoms per cubic centimeter there, as well as the fact that the atoms, on average, are going to be more in the way of denser elements. So keep that in mind when we talk about the formation of our planets later on. So the overdense regions tend to fragment and attract even more matter. It becomes a runaway process. In fact, once gravity overwhelms gas pressure, it's essentially a free fall collapse. and that freefall collapse will end up forming stars within 10 to 100 million years. The most massive ones will form first, and then after that, the less massive ones will form. And then these different fragmenting regions will kind of separate and form stars in different areas. A lot of these stars will orbit around each other. In fact, most stars in our galaxy are part of multiple star systems. Our sun is special, it's alone. Here is a zoomed in version of that part of the Carina Nebula that I showed you earlier. So it's basically like Rudolph the Red-Nosed Caterpillar, or Red-Eyed Caterpillar. But those are the places where stars are forming. In fact, you can kind of see that happening here. And the whole thing is radiating off because you're dealing with collapsing gas and dust. Well, collapsing gas and dust gets hot. When gas is compressed, it gets hot and eventually becomes hot enough to radiate visible light. Though it's radiating more in the infrared part of the spectrum. In fact, that picture, I believe, is a near-infrared picture taken by the Hubble Space Telescope. Now, something else to keep in mind is that in terms of how these stars form, stars today, on average, tend to be less massive than those that formed in the earlier universe, because in the earlier universe, you didn't have heavy elements. You had hydrogen, helium, and tiny amounts of lithium, and that was it. So there are two problems with that. First, if you're trying to quickly collapse and form stars, well, you don't have these nice, dense, heavy fragmentation nuclei, so to speak, in which these gas clouds are going to collapse. In other words, the collapse is going to be very slow. And there's also another thing. As the collapse happens, remember, the gas heats up. Well, what does a heated up gas do? It creates more gas pressure. More gas pressure. That's going to slow the collapse. In fact, if there's no way at all to radiate that heat off, the collapse will cease before any stars form at all. Now, it turns out that molecular hydrogen is able to radiate off that heat, and there was molecular hydrogen around in the early universe, because after all, there was hydrogen. So if the area gets dense enough, you're going to form molecular hydrogen. However, molecular hydrogen is much less efficient at radiating off heat. So as a result, because of the fact that this collapse is going to be much more slow with these giant molecular clouds early in the universe than it is now, by the time you get stars forming, these overdense regions, these fragmented regions, will have had time to merge together. So instead of having a giant molecular cloud form, say, like 1,000 little stars, which is fairly typical today, instead, it'll form a few really massive stars, ones that become supernova and that produce heavy elements that end up going into the rest of the universe and seed future star-forming regions and cause them to collapse more quickly. So yeah, as time goes on, you get more and more of these heavy elements, which allows for more and more star formation, but the stars that do form tend to be smaller. So, in any case, yeah, back in the early parts of our universe, you had lots of really massive stars, like 300 solar mass stars, exploding into supernovae. Now, in any case, once the fragmentation goes down to an individual star, finally, after a while, the star will get enough heat in the center to start fusing protons with each other to form eventually helium nuclei, a process that we'll discuss in more detail later in the course. And meanwhile, the rest of the system is in orbit around that star, because generally speaking, any giant molecular cloud or anything like that is going to have some little bit of rotation, just random rotation. Some will go one way, some will go another way, etc. But as it collapses by gravity, conservation of angular momentum means that it's going to start rotating faster, just as an ice skater spins faster upon drawing in the arms. Same thing happens here. But as it rotates faster, you're going to start to get more and more collisions between these gas and dust particles, and there's going to start to form what we call protoplanetary disks. And this is a picture of one of those in the Orion Nebula, picture taken with the Hubble Space Telescope. So you get these protoplanetary disks, which themselves have masses ranging from about 0.001% and 0.3% of our sun's mass. But on the high end, that's enough to form a few Jupiter mass planets. So that's something to keep in mind. Now, the fact that we see very few of these that have the high part of that mass means that systems that have planets with, say, like 10 Jupiter masses, those 10 Jupiter mass planets formed very quickly, like pretty much at the same time as the star, before you really got a whole lot in the way of a protoplanetary disk. Typical radii of these disks are between 100 and 200 astronomical units. In other words, relatively similar to the size of the Kuiper belt in our solar system. Interesting. Now, these past few slides were more about people who are curious about some of these details and want to keep them in mind as we're trying to understand our solar system. Just keep in mind that we're going to discuss star formation in a lot more detail later in the course. So now, let's discuss how planets form around stars. Because observations tell us that at least 50% of newly formed stars, that is protostars, or newly forming as stars, protostars, are surrounded by disks of material. So these protoplanetary disks, or proplyds as they're often called, are quite common. Here are some more pictures of some of these protostars with their associated disks in the Orion Nebula. Now, these disks will eventually kind of flatten themselves out a little bit, but before that happens, you're dealing with something that's a torus, which is really the mathematical form of a donut. So as it continues to collapse, it starts spinning faster, but this faster spinning means more interactions. So what happens is particles that are interacting with each other in the direction of motion of spin of the disk then tend to kind of bounce off of each other and cast each other in or out of the disk. So the disk becomes wider as this continues happening. But it also becomes flatter because collisions that happen in the vertical direction relative to, say, the plane of your donut, so to speak, they tend to cancel each other's velocities out. So as time goes on, the disk becomes flatter as the particles continue interacting with each other with these collisions. So some get cast inward, some get cast outward, but overall it becomes thinner. Now, when these particles collide with relatively low-speed collisions, which is often the case, they combine with each other because they generally have relatively jagged shapes. This is a picture of a typical interplanetary dust grain. So these things are quite jagged, so when they interact with each other, they stick. They stick. This process of growing by collisions is called accretion, and it's the primary process by which small objects form out of disks of gas and dust when this term, or when the solar system is forming. Now keep in mind this accretion term. You'll hear it a lot in science. In fact, you've probably already heard it before when talking about black holes, but the accretion disks around black holes are very different in nature than the accretion disks around newly forming stars, so that's something to keep in mind. So in any case, these dust grains collide and stick together, and when a larger dust grain collides with another larger dust grain, it forms even larger dust grains. And when even larger dust grains collide with each other, they form sand grains. And when little sand-type grains collide with each other, they form even larger sand grains. Now keep in mind, these are very different than the typical sand grains you see at the beach. They're not cubical in shape. They have these other jagged shapes which make them easy to stick together when they collide. Also, a lot of times they are electrically charged due to having participated in ionization reactions with ultraviolet photons in the newly forming disk and stuff like that. So that makes sticking together even more likely, because if one of them is charged and the other is neutral, then polarization will cause them to stick together. That's why rubbing a balloon in your hair and sticking it onto a wall works. So in any case, yeah, larger sand grains forming and bumping into other larger sand grains form small pebbles. And this continues on up until eventually you get planetesimals, which are objects that have enough mass that they have enough self-gravity that they grow more rapidly by pulling in other objects because of their gravity than they do by random collisions. Now, they still pull in still grow by random collisions. It's just that once you reach the size of about 1 kilometer, the rate at which the size increases suddenly grows very dramatically because of increasing gravity. So, the thing is, though, there is something weird going on between about the size of a boulder and the size of a planetesimal, because boulder-sized objects, in spite of the kind of sticky shapes of the dust particles that make them up, when they collide with each other in these types of environments, they're just as likely to bust each other apart as they are to grow in size. Nonetheless, we do see these types of interactions occurring when we look at other stars, at other newly forming stars. So we know that our general idea is correct, but in terms of the exact physics that's going on, it's hard. We think it has something to do with magnetic fields because we have not only found in our simulations but also observed evidence around newly forming stars that you have certain eddies, certain areas like vortices in these regions where material formed of larger objects seems to be kind of clumping together, and that's kind of a signature that magnetic fields of the newly forming star are involved, and these magnetic fields can help to kind of even out the velocity dispersion in some of these eddies so that eventually you just get enough material kind of circling in these eddies that its own self-gravity slowly causes it to pull in and collapse, and you quickly end up getting planetesimals. So in any case, yeah, we know that we get these objects, but we're still working on really the final stages of understanding the picture of exactly how you go from boulder-sized objects to planetesimals. But we know it happens because we see it happening. Now, you might be thinking, well, wait a second. Doesn't this sound kind of like how rings get formed by tidal forces pulling things apart? Well, here's the thing. Rings happen because of tidal forces pulling things apart. But a star is so big that the actual tidal forces from that star that would be capable of pulling these newly forming planetesimals apart are much closer to the star than where the planets typically form. So the regions around the stars where the planets form have very low tidal forces. So even though the gravity overall is very strong, the gravity doesn't change a whole lot with respect to position once you get reasonably far away from the surface of the star. So something to keep in mind. So an artist's depiction of some of these stages here. And here's an actual picture taken from the Subaru telescope where you can see these kind of spiral arms being formed because of really the gravity of a newly formed planet carving out certain regions. And now some other images to show you. Here we have a 5 to 14 Jupiter mass planet. This is kind of, think of this as a 3D image where the planet's kind of going into the slide and then it would come out over here, and it has also kind of carved out its region. This whole idea of carving out the area near where it orbits is very important for talking about planet formation and the completion of planet formation. That's something that we're going to come back to when we talk about Pluto. Long story short, Pluto never really finished forming. And here's an awesome observation from the ALMA radio telescope showing a lot of these rings having been carved out by these newly formed bodies. And here's an artist's depiction of this. Here's what I really like about this picture. I'd been showing this picture for a very long time, but it's very similar to this much more recent image from ALMA right here. So, in any case, here's some more pictures taken from the ALMA Observatory of these disks around newly formed stars, often showing these rings and spiral structures formed by planets that have kind of carved out their orbits. The planets are hard to see because they are radiating at different wavelengths, but nonetheless you can see their effects. Now, looking at the formation of planets in more detail in our solar system is going to lead us toward an understanding of why our planets are the way they are, and why, in particular, Jupiter is the most massive planet. And we will get to that in the next video. So I hope to see you then, and thank you for watching.